Alright, let's look at some examples from 4.2. I think most of the first ones you should have not much trouble with picking out the graphs. Let's look at a couple other ones. Let's start with number 16, just to get an idea kind of what we're doing here. We have a function f of x, and notice that this is a linear function. It's 3 minus 2x, and we're given a domain here, or at least an interval where we're defining our function, or all we're concerned about is x being less than or equal to 5. We're supposed to sketch the graph of this and use a sketch to find the absolute local max and min values for f. Now, notice that if we sketch a graph of this thing, this is just a line with a y-intercept of, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, a y-intercept of 3 and a slope of negative 2. So we're going to go through the point 0, comma 3, and then down to the left 1. I'm sorry. How about down 2 to the right 1, since we have a negative slope here. Down to, let's see, to the right 1, and so on. Down 2 to the right 1. So you can see this is what our line looks like. And again, we're stopping where x is equal to 5. We're just looking at x's that are less than or equal to 5 here. So our line goes infinitely far in this direction, but it does stop at this point right here. Well, what is the absolute max value? Well, absolute max, is there a biggest point? No, there's none, because we can keep going to the left as far as we want, and our line keeps going up, our function value keeps getting bigger. So an absolute max. How about an absolute min? Sure, we have an absolute min. It's at the point right here. It's where x equals 5, and you can see that f of 5 is equal to 3 minus 2 times 5, which is 3 minus 10, which is negative 7. So the absolute minimum value is this right here. Negative 7 is the absolute min value. Now, what about local max or local mins? Well, local maxes and local mins occur where our derivative is equal to 0 or undefined. Now, if you take the derivative of this, you get 0 minus 2. Just get a negative 2. When is this equal to 0? When is negative 2 equal to 0? Oh, yeah, negative 2 is not equal to 0 because negative 2 is too busy being negative 2. So that means we have no critical values or no critical numbers, and that means no local max or min. No local extrema. No local extrema or local max or min. Alright, so you can see the derivative is never 0 because our function never makes a turn. There's never, the line tangent always has, well, the line tangent is always the same as the line itself. The line tangent always has a slope of negative 2. It never has a slope of 0. So just the absolute min value of negative 7, which occurred at x equals 5. No absolute max, no local extrema, no local max or min either. That's 16. Let's try another one. Okay, let's look at some where we're trying to find the extrema or find the critical numbers of the function. For example, number 24, we have the function f of x, and it's equal to x cubed plus x squared minus x. We want to find the, what are we doing here? Find the critical numbers. Okay, so remember that the critical numbers are any values in our domain where the derivative is undefined or the derivative is equal to 0. So let's take the derivative. Should be getting pretty good at this now, especially for polynomials. We have 3x squared plus 2x minus, remember there's a 1 here, so minus 1. And we want to find out where does this equal 0. You can see it's always defined, so there's never any critical numbers where this derivative is undefined. This is a polynomial, it's always defined, so we don't have to worry about that. Let's see, let's set this equal to 0. Well, we're going to have to use the quadratic formula. This may factor. Let's see if we can get it to factor 3x and x. We have to do 1 and 1. It's just a matter of positive and negative. We can get that to work out. And I think if we go, yeah, positive 1 here, negative 1 here, right, that'll give you a 3x minus x is a positive 2x, 1 and negative 1. Sure enough. So we got 3x minus 1 equals 0, or x plus 1 equals 0. So x is either 1/3 or x is negative 1. So we have these two critical numbers. Now, are they maxes or mins? Well, we'll try and figure that out in future problems, but for right now, these are our two critical numbers. We can look at a graph of this function and see if they're maxes or mins. If we put our function in, it was x to the third plus x squared minus x. Yeah, there's the graph here. You can see we actually do have a local min, and it occurs right here, a little past 0, between 0 and 1, but closer to 0. Another one at negative 1, and that was our two those were our two critical points. One was at -1, the other one was at a positive 1/3. So it turns out positive 1/3 gave us a local min, -1 gave us a local max. They're neither global maxes or mins because obviously we have points getting much bigger here to the right, points getting much smaller to the left. We'd have a local max at -1 and a local min which occurs at positive 1/3, and we had found those critical points again by taking the derivative and setting it equal to 0. Now let's try another example. Let's try number 32. We got a function capital G of x, and it's equal to the cube root of x squared minus x. Alright, so we're going to take the derivative of this, and again, as we've said, anytime you got a radical, dude, and you want to take the derivative, you want to rewrite that radical with rational exponent notation. So this will be the quantity x squared minus x to the 1/3. Let's take the derivative here. We're going to do a little chain ruling. Bring the 1/3 down in front, leave what's inside alone. Reduce the power by 1, that's a -2/3 now, times the derivative of what's inside. Derivative of what's inside is going to be 2x minus 1. Okay, so let's see if we can simplify this a little bit. We have 2x minus 1 over, remember this 3 is in the denominator, and this negative exponent is going to be x squared minus x to the positive 2/3. We want to find out, well, this is our derivative right here. So our critical values are going to be where this thing equals 0 and where it's undefined. So g prime of x equals 0 would mean that, well, the only way a fraction can be equal to 0 is if its numerator is equal to 0. 2x minus 1 is equal to 0, which means x is equal to 1/2. Alright, so there's that. Now, what about over here, g prime of x undefined or does not exist? Well, that's going to be where the denominator is equal to 0. So where is 3 times the quantity x squared minus x to the 2/3 equal to 0? Well, that's just going to be where x squared minus x is 0. And if we factor out an x here, you can see that'll occur in two places, 0 and 1. So we have a critical number at 1/2, that's where our derivative is equal to 0, and then two more critical numbers, both at 0 and 1, where our derivative is undefined. Let's take a look at this graph and see what it looks like. Well, I'm not crazy about how the graph of this turned out. I think there's a mistake here. It's having trouble graphing between 0 and 1. You can see we do have where the derivative is undefined at 1 and the derivative is undefined at 0 because of these sharp turns here in the graph. But there should be some part of the graph here between 0 and 1, and we should have a critical point at 1/2, and we're just not seeing that. And I'm not sure why that is, but we do have three critical numbers, 0 and 1, the two places again where the derivative is undefined or does not exist, and 1/2 is the critical number where the derivative is equal to 0. Alright, let's try some other types of problems then. Actually, let's look at 36. Now let's try 33. At least set up 33. For number 33, we have a function f of theta. It's equal to 2 cosine theta plus sine squared of theta. Now again, we're looking for the critical number, so we're going to take our derivative, f prime of theta. So the derivative of cosine is, what's that? Yeah, negative sine, so it's going to be -2 sine theta, plus the derivative of sine squared, it's going to be 2 sine theta times the derivative of what's inside. Derivative of sine theta is cosine theta, so the chain rule there. Alright, so this thing is going to be defined everywhere. You can take the sine of any value, any real number, and you can take the cosine of any real number. So there's no place where our derivative does not exist. So the only place we're going to get our critical numbers is where our derivative is equal to 0. Now I can factor out a 2 sine theta out of both terms, and so I get -1 plus cosine theta equaling 0. Now where is sine theta equal to 0? Well, where is 2 sine theta equal to 0? So we have the zero factor property, right? Two things multiplied together equals 0, means one of those things has to be 0. Well, 2 sine theta will be 0, wherever sine theta is going to be 0. Where's sine 0? Well, remember what the sine function looks like. Sine function looks like this. And it's 0 at 0, and then pi, and then 2 pi, 3 pi. So it's basically going to be where theta is equal to any multiple of pi. Any multiple of pi and sine is going to be 0 at those points. So n times pi, where n is equal to some integer. Now the other possibility where we could have the derivative come out to be 0 is where -1 plus cosine of theta is equal to 0. Adding 1 to both sides, that's going to be where the cosine of theta is 1. And so theta then is going to be the inverse cosine of 1, where is cosine equal to 1? Well, let's remember what the cosine function looks like. Cosine function looks like this. So cosine function is 1 here at 0, and then again at 2 pi, and then again at 4 pi, and so on. So here it's going to be wherever theta is equal to 2 in pi, wherever n is any multiple of pi. But we've already got those covered basically with these. 2 pi is where sine is 0, but it's also where cosine is equal to 1. So really, any multiple of pi will get the job done. That's where critical values or critical numbers are. Any multiple of pi for theta will make the derivative come out to be 0. And you can see that here, at least for part of it here, when theta equals 0, where it have a line tangents horizontal. When theta equals pi, a little bit past 3.14, we have a line tangents horizontal. Negative pi, line tangents horizontal. 2 pi, we would have a line tangent horizontal, and so on. So that bears out in the graph. All right, let's look at a couple more problems then. Let's look at some where we want to find the absolute maximum and minimum values on f on a given interval. Let's start with, I don't know, how about 43? We can at least get that one set up. So that's the highlighter. Let's try this. Here we go. 43, we have the function f of t, our independent variable here, and it's equal to t times the square root of 4 minus t squared. And our interval here that we're looking at is from -1 to 2. So remember, our steps for finding absolute extreme, absolute maxes and mins. First thing we're going to do is find our critical points, and then we're going to check our function value at our critical points and our endpoints at -1 and 2 and see which one's the biggest value, which one's the smallest value. So before we take our derivative here, let's rewrite our radical dude as a rational exponent. So let's do it like that. Now let's take our derivative. F prime of t. Hey, we're going to have to use a product rule here. We got a first function and a second function. So let's take the first times the derivative of the second. Here's a chain rule on this. I have a quantity to the 1/2 power, so it's going to be 1/2 times that quantity to the -1/2 power times the derivative of what's inside. Derivative of 4 minus t squared is just going to be a 0 minus 2t, or just a -2t. Alright, so there's first times the derivative of the second, plus the second left alone, which is 4 minus t squared to the 1/2, times the derivative of the first, which is 1. Alright, so it's kind of an ugly derivative. Let's see if we can simplify it a little bit. What do we have? Let's see, we got this 2 and this 2 divide to 1, so we're going to have, well, here's a t times a t. Those are both on the top level. A -t squared divided by this -1/2 will drop it into the bottom. So 4 minus t squared to the 1/2 plus just 4 minus t squared to the 1/2. Alright, we want to find out where does this equal 0 or is undefined. Well, let's start off where does equal 0. F prime of t equals 0 implies that -t squared over 4 minus t squared to the 1/2 plus the quantity of 4 minus t squared to the 1/2 is equal to 0. And so let's look at this equation here. I think to make this a little bit simpler, what I'm going to do is get a common denominator here. So I'm going to multiply both top and bottom by 4 minus t squared to the 1/2 power. So I have, let me just rewrite what I'm doing here. 4 minus t squared to the 1/2, or the square root of that, plus the quantity 4 minus t squared to the 1/2. And I'm going to do is I'm going to multiply both top and bottom of this one by 4 minus t squared to the 1/2 power to get a common denominator to combine these two things. So that's equal to that, which is going to be equal to then a -t squared plus, well, I take this quantity to the 1/2 times this quantity to the 1/2, I just get that quantity. So I get a 4 minus t squared all divided by that common denominator, 4 minus t squared to the 1/2. This is a better way to look at our derivative. So actually we have a 4 and 2 negative t squareds there, so 4 minus 2t squared over the quantity of 4 minus t squared to the 1/2. Now, if that is equal to 0, that means that the numerator is going to have to be 0, which means 4 is equal to 2t squared, which means t squared is 2, which means t is either the positive or negative square root of 2, but the negative square root of 2 is actually going to be less than -1. Remember that -1 was our lower limit here. So the negative square root of 2 is out, and we're just going to use the positive. So our critical point here, from where if f prime of t equals 0 at t equals the positive square root of 2. Alright, and again, it also equals 0 with negative square root of 2, but that is not in the domain that we were given. The interval we were given between negative 1 and 2. Negative square root of 2 is less than negative 1. So we only take critical points that are in our interval. Now, where is f prime of t not defined? Alright, well remember that f prime of t, when we simplified it here in this last step, it was 4 minus 2t squared over, what was it, the quantity of 4 minus t squared to the 1 half. Well, this is going to be not defined where the denominator is equal to 0. So basically we're asking, where does 4 minus t squared to the 1 half equal to 0? So wherever our denominator is 0, that means we're not going to be defined there. Well, if we square both sides, we're just looking for where 4 minus t squared is 0. That's where 4 is t squared. That's where t is plus or minus 2. Let's see, again, positive 2 is in our interval, but negative 2 is not. So we're going to throw out negative 2, and we're just going to say then, we're just going to take the positive here, and we're going to throw out the negative. Let's try that again. Alright, so where's that prime of t not defined? At t equals positive 2. And again, negative 2 is not in our interval. So we have 3 points to check. What are our 3 points to check? We have 2. We have t equals 2. That was where our function was undefined. We have t equals the square root of 2. That was where our function was, our derivative was equal to 0, I should say. Derivative was undefined. Derivative was undefined at 2. Derivative was equal to 0 at square root of 2. And then we also have our endpoints to check, negative 1 and 2. Well, 2 is doing double duty. It's an endpoint and it's a critical number. So we only need to check that once. So let's remember what f of t was in this problem. F of t in number 43 was t times the square root of 4 minus t squared. So let's start with f of negative 1. That was our left endpoint. So that's going to be negative 1 times the square root of 4 minus negative 1 squared. That's equal to negative the square root of 4 minus 1 squared. 4 minus 1 is 3. So that's negative square root of 3. Let's try f of 2, our right endpoint, which is also where our derivative was undefined. So it's also a critical value. That's going to be 2 times the square root of 4 minus 2 squared. 2 squared is 4. That's going to be 0. Alright, so far, negative square root of 3 is our local min, or absolute min, rather. And let's see, then we had one critical value in our interval. That was the square root of 2. That was where our derivative was equal to 0. So that's the square root of 2 times the square root of 4 minus the square root of 2 squared. We put that in for t here. So we get the square root of 2 times the square root of 4 minus the square root of 2 squared is 2. So we get the square root of 2 times the square root of 2, which is equal to 2. Well, what's the biggest value we find here? The biggest value is 2. What's the smallest value? The smallest value is this negative square root of 3. So we can conclude then that f, doing that a lot lately, f has a, not a local, but an absolute max of, the max value is 2. It occurs at the point x equals the square root of 2. F has an absolute min of negative square root of 3, and it occurs at x equals negative 1. Let's take a look at the graph of this thing. So here's the graph. X times the square root of 4 minus x squared. I had to put x in place of t, because that's the independent variable this program recognizes. And notice I cut off x here from negative 1 to 2. Where's our absolute min value? It's at negative 1. And it's this negative value, we said the absolute min was negative square root of 3 at x equals negative 1. So that's our y value at this point, negative square root of 3 at x equals negative 1. Absolute max we said occurred at square root of 2 about right here, and had an absolute max value of 2. So that's that max value of 2, and that's at x equals the square root of 2. So it looks like it bears out exactly what we found algebraically. Alright, let's go ahead and we'll just at least set one more up here, kind of running along here, but we'll look at number 48, where we're doing the same thing. Find the absolute maximum of the function f of x, which is equal to x minus the natural log of x, on the interval from 1/2 to 2. Remember, the natural log is only defined for positive numbers. So let's take our derivative, f prime of x, and that's going to equal 1 minus, remember the derivative of the natural log is 1 over x. So first of all, let's find out where that equals 0. Well, that's where 1 is equal to 1 over x. And so cross multiplying here, that's where x is going to have to be 1. So our derivative is equal to 0, where x is equal to 1. That's in our critical, that's in our interval. So that's in. Where is f prime of x not defined? Well, if you look, it's not defined at x equals 0. And 0 is not in our interval from 1/2 to 2, so we don't have to worry about that number. So we basically have to check those 3 points. You're just going to check f of 1/2, you're going to check f of 1, and you're going to check f of 2. And the biggest one is your max, the smallest one is your min. I'll let you guys take care of that. Alright, so again, you can take it from there. Just check your function at each of those values, your 2 endpoints and your critical number of 1. And again, the value that gives you the biggest number, that's your absolute max. It occurs at whichever point you put in there, and your absolute min is the smallest value. Alright, so we're done with 4.2. You should be in good shape. Homework password for 4.2. 4.2, it's a good one. I think you're going to like it. It's turpitude. Turpitude. And basically what it means is depravity. So don't have turpitude. Turpitude. Good luck, and let me know if you have any questions.